Mrs. Wise here. This is part 2 of the geology passage. We are on the very last paragraph of that first column on page 99. All right. Geologists settled the rock dispute largely as a result of the work of Nicolas Desmarest, a French geologist. In the 1760s, Desmarest had shown that the basalt rocks of the Auvergne region of south-central France were created from lava. In the early 1800s, two of Werner's most famous students, Leopold von Buch and Alexander von Humboldt, visited several volcanic areas. Those areas include the Auvergne region and Mount Vesuvius, a volcano in Italy. After studying rocks in those places, the two became Plutonists. Experimental geology began as a result of the friendship between Hutton and Sir James Hall, a Scottish geologist and physicist. Hall became interested in verifying Hutton's ideas experimentally. He melted rock in large furnaces, much as rock melts far beneath the Earth's surface. He found that melted limestone cools to form marble. Hall's work led to the acceptance of Hutton's idea that granite is formed from magma. So he tested to see, can rock be melted? And when it did, and it cooled and it formed it, it was like, oh, okay, so they figured out magma. William Smith, an English civil engineer, was the first person to use fossils to map rock strata. While surveying and building canals in southern England during the late 1700s, Smith had seen layers of rock that contained fossils. He discovered that the same kinds of fossils occurred in the same strata, even in different locations. He then used fossils to trace rocks to the same age across large areas. In 1815, Smith made the first geological maps showing the strata of England. So he was looking, remember we learned the strata are the different layers, and he was looking and noticed that if I see this type of fossil in, let's say, the third strata down here, then even if I go way over there, I see the same type of fossil in the third strata down. And so then you could use the different fossils and the different strata to map, how far back that period was. In 1830, British geologist Sir Charles Lyell completed the first volume of a 3-volume textbook called Principles of Geology. Lyell's book greatly influenced other scientists. Lyell supported Hutton's principle of uniformitarianism. Louis Agassiz, a Swiss-born naturalist, studied European glaciers in the 1830s and 1840s. He suggested that a huge sheet of ice had once extended from the North Pole to Central America, or Central Europe. Agassiz explained how the slow-moving fields of ice changed Earth's surface. So he started figuring out how the glaciers changed. We learned earlier that's one of the ways the Earth changes, right? So this is the guy who figured that out. In 1846, Robert Mallet, an Irish-born engineer, began the scientific study of earthquakes. He measured gunpowder under the ground, or he exploded gunpowder under the ground, and then measured how rapidly the resulting vibrations traveled through the rock. So this guy is brilliant. To study earthquakes, he would explode gunpowder way, way down in the earth, and then he would measure how long it would take for the vibrations to come up to the top to figure out how deep the earthquakes were and to study earthquakes. That's kind of cool. In the New Zealand-born physicist Ernest Rutherford suggested in 1904 that the half-life of radioactive chemical elements in minerals could be used to determine the age of the minerals. The half-life of an element is the length of time needed for half of the atoms in a sample of the element to decay. Arthur Holmes, a Scottish geologist, was one of the first scientists to use radioactivity to determine the age of rocks. So they started to learn that as they studied how radioactive rocks were, they could figure out how old they were. In 1927, he included a geological time scale in the book, The Age of Earth. All right, before we switch to page 100, let's look at the little caption next to this picture. It says, a petroleum geologist has just set off an explosion in the search for petroleum. Sound waves from the explosion will travel through the layers of rock and then bounce back to the surface, where an instrument called a seismograph will measure their speed. Sound waves travel at different speeds through different materials. Thus, this measurement will help the geologist determine whether layers of rock might contain oil lie below. So just by figuring out how fast the waves travel to the top, they can figure out what's underneath the rock, and they can figure out if there's oil there. All right, let's tackle page 100. Yeet, scooch over. Under this picture, it says hydrographers use a sonar transducer to obtain information about undersea earthquake activity. This instrument uses sound waves to create a diagram of the ocean floor. So they're using sound to map out the ocean floor where they can't see. In 1868, a group of scientists proposed the Earth's outer shell consists of a number of rigid plates that are in continual motion. This theory is called plate tectonics, and it helps support the idea that the continents move about on Earth's surface. It also helps explain the occurrence of mountains, volcanoes, and earthquakes. In science, you've probably studied plate tectonics, and it's the idea that the crust of the Earth is made up of these solid plates that are slowly moving over time. You may have seen a map and seen how nicely all the continents fit together, like maybe it was all one landmass and it broke up over the millions of years. And that's just, it explains earthquakes, it explains mountains, it explains volcanoes. All of that makes sense if you subscribe to the plate tectonic theory, that there's these plates that are moving and bumping against each other and breaking apart and things like that. All right, we're in the bold on the first column, Geology of the Solar System. Geology of the Solar System. Until the late 1950s, scientists could not gather much information about the geology of other objects in the solar system. The only tools available for observing those objects were ground-based telescopes. Earth's atmosphere creates a blurring effect that limits the sharpness of images from such telescopes. In addition, the planet Venus presents another barrier to observation. It is surrounded by thick clouds of sulfuric acid that block views of the planet's surface. So they had trouble studying other planets because our atmosphere made it hard for telescopes to see through it. And then, like, Venus has all these clouds around it, so even if they could see through it with a telescope, they couldn't see past the clouds. The space age created a new field called planetary geology, the study of other objects in the solar system. That age began when the Soviet Union launched the satellite Sputnik in 1957. In 1959, the Soviet space probe Luna 1 flew within 3,700 miles, or 6,000 kilometers, of the Moon. Sensors on the probe gathered scientific data, and radio transmitters sent the data to Earth. Since then, several space probes have orbited the Moon or landed there. Astronauts first landed on the Moon in 1969, and they brought moon rocks back to Earth. Probes have orbited and landed on Venus and Mars, and a probe has flown past Mercury. In 2001, a space probe made the first landing on an asteroid, an object called 433 Eros. So planetary geology is still studying planets or things like that. It's objects in space. And we've sent probes to the Moon. It says we've sent probes to Venus and Mars. We sent a probe past Mercury, didn't land on it, but got close enough to get some data. And we've even landed on an asteroid to get information about that. Space probes have also studied the gas giant planets, Jupiter, Saturn, Uranus, and Neptune, and their major satellites. The planets are not subject to geological study because they consist mostly of gases and liquids. However, the planet's satellites are made of rock and ice, and so they are much more interesting to geologists. So some of the planets are mostly made up of gas, so they're hard for them to study. They're not tangible, but their satellites, the things around them, are made up of rock and stuff, and so planetary geologists can study that. To interpret the information sent to Earth by space probes, geologists use their knowledge of processes that occur on Earth. For example, they apply what they know about volcanoes on Earth to the study of Jupiter's satellite, Io, the most geologically active satellite in the solar system. Geologists also apply what they have learned about other objects to the study of Earth. For instance, studies of the Moon showed how meteorite impacts help shape the Earth's surface. So they use what we know about Earth to study those planets, and then they find out things about those planets or those things in space that help them understand the Earth too. All right, our last section is careers. I'm on the second column of page 100. Geologists hold a wide variety of jobs in industry, education, and government. They explore for coal, oil, gas, uranium, and other materials that supply energy. They look for deposits containing such metals as copper, gold, iron, lead, silver, and tin. They also try to find diamonds, emeralds, rubies, and other gems. So some geologists, are looking for things in the earth, the things that are worth money, right? Geologists locate building stone, clay, and underground water. They create maps and interpret aerial photographs. They also supply information on how to maintain our water supply and keep it from becoming polluted. Geologists contribute to space exploration by interpreting images of planetary surfaces, data that indicate the chemical makeup of those surfaces, and rock samples from the moon and other bodies. So those are all different things geologists can do. Job opportunities. Most geologists work for private companies. Some of the companies explore for oil and gas or for minerals. Other companies work on environmental issues such as water management, waste disposal and cleanup, and land use planning. Geologists also conduct research and teach at colleges and universities. So most work for companies that have a purpose and they work on that purpose, or they might work at colleges and be like teachers or study their field. Areas of specialization. In geology are many. Petroleum geologists search for oil and gas deposits on land and on or beneath the ocean floor. Their tasks include mapping, fossil studies, and analysis of rock structure. And underneath it, it's got a picture of a paleontologist, it says. A paleontologist studies fossils found in rocks. The findings provide geologists with information about the age of the rocks and about the land or water in which they were deposited. All right, last page. Mining geologists look for materials other than gas and oil. They often work in underground or open pit mines. There they examine deposits and direct ore removal. Specialists called paleontologists study fossils to learn about life in prehistoric times. Petrographers classify rocks. Stratigraphers deal with the arrangements of layers of rocks to determine their age and history. Mineralogists study and identify minerals. Geomorphologists study how Earth's surface was formed and how it changes. Geophysicists study Earth's interior using waves from earthquakes or from explosions. In addition, geophysicists investigate Earth's magnetic, electrical, and gravitational properties. And then it tells you who wrote the article and some other articles you could read if you were interested in it. So that last paragraph is just telling us about some of the specialty areas that geologists might work in. All right, well, this was specialty properties. Let's see. Yeah, so this was quite the article. I hope you say enjoy it. I know nonfiction is not everybody's thing, but it did give us a little bit of background about geology. Remember, the quiz is open book, so you'll be allowed to use your paper, but this hopefully gives you some idea of what it was talking about and where it was at, and we'll go on from there. Good luck on the quiz. If you have any questions, come see me before or after school.